Okay, hi everybody. Today we are going to talk about nuclear physics, and this is one of the most important and interesting chapters. It's really critical to just understanding the universe. Why is the universe the way it is? Why are the atoms and elements that we see around the universe there? It's also really important in modern physics research and also really critical in a lot of different applications and also in medical science. This first slide just shows some neat applications of nuclear physics. On the top left, we have a tokamak. This is a kind of modern edge of knowledge type research in terms of fusion. So what you see here on the left side of the picture is the actual tokamak, and on the right side you can see it in operation. This little color insert, you can see the colored plasma trying to create fusion within this reactor. Here we can see a modern nuclear power plant on Lake Michigan. Of course, the sun gets its power through nuclear physics. This is a look at an actual nuclear reactor. You can see the glowing blue from the Cherenkov radiation. Here we have, using nuclear physics to date, archaeological findings, another really important topic. Of course, in medical science, things like MRIs are all based on nuclear physics. And then on the left here is a modern nuclear physics collider laboratory. This is the Brookhaven National Lab on Long Island in New York. And what you see here is a particle accelerator. But what they are accelerating in this case is nuclei. And they're smashing them together in different detectors such as Phoenix and STAR. And they're seeing what comes out. They're trying to understand the nucleus and the strong force and what holds all the nuclei together. And this is what an actual collision looks like at one of these detectors. So you can see thousands of particles flying out from one of these collisions. So there's all sorts of really neat things going on in the world in terms of nuclear physics. So let's just do a quick introduction, and then we'll do a second video for the next part of this chapter. And just to reiterate how important nuclear physics is, if we really want to try to understand the material basis for the world, why do we see certain elements around us and not others? It's all about nuclear physics. So this is a really interesting plot. It plots the relative abundance of certain types of atoms, certain elements, right? And it's basically compared to silicon. So it says for every million silicon atoms you see, right, you see maybe, let's pick copper. You see about 100 copper atoms. So silicon is a lot more abundant than copper. Right? For every million silicon atoms in the universe, there's about 100 copper. And for every million silicon atoms in the universe, there's maybe 10 to the minus 3 gold atoms. So gold is really rare. So if we want to try to understand why are some elements so common, things like oxygen, aluminum, silicon, nickel, sodium, potassium, calcium, things like that. I'm sorry, nickel is down here, so sodium up here. Why are these so abundant? Why are these so common in our universe while other things are so rare, right? Things like gold and things like that. So we're going to try to understand that in this chapter. Okay, a little bit more introduction, and of course you probably know this, but let's take a closer look at the atom. In the previous chapters, when we were trying to understand quantum mechanics, we talked about the electron in this bound state forming the orbitals around the nucleus. So now we're going to try to focus on the nucleus. So the nucleus is this kind of ball in the middle of the atom. You can see the relative size difference. An atom is about the size of 10 to the minus 8 centimeters. Nucleus is 10 to the minus 12 centimeters. So it's a tiny fraction of the volume of an atom is taken up by the nucleus. Okay, the nucleus, you can see, is composed of basically two types of particles, colored here with red and black. I don't know what color they actually are, but here they're colored in red and black. And so the nucleus is composed of protons that are positively charged and neutrons, which are neutral. All right, they don't have any net charge. And we now know, we're going to talk about this in future chapters, that the proton and neutron, which are particles, are actually composite particles, which are made out of other particles called quarks. Okay, so, but for this chapter, we're mostly going to be focused on protons and neutrons and the nucleus. And just collectively, we call protons and neutrons nucleons. So the particles that make up a nucleus, we call nucleons in general. So I'll probably use that term a lot. Now let's talk a little bit about some notation. Again, you've probably seen this before, but let's make sure we're clear on it. When we're talking about different elements, we tend to use this notation where the X here represents some chemical element. right? So it's whatever the symbol in the periodic table is. So for example, it could be beryllium, Be, right? Next, on the lower left to the symbol, we typically put the atomic number, which we use the symbol Z for, which is just counting the number of protons. Right? So beryllium, its atomic number is 4, meaning it has 4 protons. Right? And this is what makes beryllium beryllium. Right? It has 4 protons. Not included in the symbol, but I still want to note it, is we sometimes use the symbol N for the number of neutrons. And then finally we have A, which we usually put in the upper left of the symbol. This is the number of nucleons. Right? So this is the total number of protons plus the total number of neutrons. And so we typically put that up here. So for beryllium, there are 9 total nucleons. There are 4 protons. That means there are 5 neutrons. Right? So you can always figure out the number of neutrons just by subtracting. And sometimes this symbol A, the number of nucleons, is given the name the mass number. And I'm going to explain that in a moment. Before we do so, let's just take a look at some common elements. We have hydrogen. Hydrogen has 1 proton, so atomic number is 1. Has 0 neutrons, so its neutron number is 0. So its mass number is just the total number of nucleons, which is just 1 proton. Okay. Something like deuterium, right, an isotope of hydrogen, has 1 proton and 1 neutron. So it has atomic number 1, but it has mass number 2. Right, we go up to helium, which has 2 protons and 2 neutrons, so it has mass number 4, etc. Okay, and we can go up to much bigger atoms like uranium. This isotope of uranium has 92 protons, 146 neutrons, and so its mass number is 238. Okay, well, now let's talk a little bit about units. Let's first define the atomic mass unit. We typically use the symbol U for this, so atomic mass unit is typically small u. Sometimes you also see it referred to as a Dalton, but much more common is the atomic mass unit. And atomic mass unit is roughly the mass of one of a hydrogen atom, roughly the mass of 1 nucleon, but we'll talk more about that in a moment. Just so to give you a scale, 1 atomic unit is about 1.66 times 10 to the minus 27 kilograms. So you see, it's this typical mass involved in an atom is very small. If we use a units we defined in the relativity chapters, 1 atomic mass unit is equivalent to 931 million electron volts, right? Mega electron volts, and then we have to do divided by c squared here because of E equals mc squared. If we want to report this as a mass, the proper unit is electron volts per c squared. In this case, million electron volts per c squared. And then finally, we could also talk about it in terms of the mass of the electron. 1 atomic mass unit is equivalent to 1,822 times the mass of an electron. All right, so you can see that the mass of an atom is much more massive than the mass of an electron. So just to now take a closer look here, how do we define the atomic mass unit? Well, it's defined to be 1/12 the mass of a neutral atom of carbon-12. Okay, so if I look at carbon-12, it has an atomic number of 6, it has a mass number of 12, that means it has 6 neutrons, so there's 12 total particles inside carbon, there's 12 nucleons, right? And so we define the atomic mass unit to be 1/12 the mass of carbon-12, which means carbon-12 has exactly 12 atomic mass units of mass. Okay, so now we can look at other atoms. For hydrogen, for example, the atomic mass is not exactly 1, it ends up to be 1.007825. So its atomic mass is close to 1 atomic mass unit, its mass number is still 1. Right. Helium has 4 total nucleons, its atomic mass is close to 4, its mass number is exactly 4. Okay, lithium has 6 total nucleons, its atomic mass is pretty close to 6, and its mass number is 6. Okay, we can also take a look at the individual nucleons themselves. A proton has a mass just a little bit more massive than 1 atomic mass unit. It's 1.007276. And when you're solving problems in this chapter, I encourage you to keep all the sig figs you can, because often it'll be changes in those really far down sig figs that will come to be important in solving some of the problems. A neutron is slightly more massive than a proton, 1.008665 atomic mass units, while the electron is really light, right? It's 0.0005 atomic mass units. Okay, so once we've defined the atomic mass unit, we can again look at some common elements and just again confirm that in general the atomic mass of an element is very close to the mass number. It's very close to the number of nucleons in that atom. Right? And so you can see that something like two different isotopes of oxygen that both have 8 protons, but one has 8 neutrons, one has 9 neutrons. Their mass correspondingly just seems similar to the actual number of nucleons. Right? So this isotope has 16 nucleons and its mass is close to 16. Okay, so that's it for this video. On to the next one.